Hey guys, in this video I'm going to go through another example of the Hungarian algorithm. I know it is quite a tedious, tricky process and it's very easy to make an error somewhere along the way which can affect your final answer. So I'm just going to go through a second example for you if you require it. Alright, so here we have a table. A company wishes to hire 4 computer programmers to develop 4 software packages. Because of time constraints, each programmer can only complete one job. The quote's given in weeks. By the 4 programmers are here. So Adam would take 10 weeks to do job 1, he would take 16 to do job 2, etc. So we're going to apply the Hungarian algorithm here so we can work out which programmer is going to do which job to make sure it's all done in the shortest possible time. Alright, so step 2, after having drawn the table, which we have, is to perform a row reduction. So in the first row, it appears that 10 is the smallest value. In the second, it is 9. In the third, it is 13. And in the fourth, it is 10. So now I'm going to redraw the graph, or the table, sorry, with those changes made. So 0, 6, 8, and 10. 0, 5, 10, 6. Third row, 2, 0, 7, 5. And last row, 0, 15, 11, and 6. Alright, so I'm going to try and cover those zeros with the smallest possible number of edges. A little bit of a wonky line. Alright, so I can do it in minimum 2 edges, meaning I can't move on to that final step because we need the number of edges to be equal to the number of tasks. So we need to be able to do this in minimum 4 edges, which at the moment we're not, we're doing it in minimum 2. Which means we will need to apply a column reduction. So I'm just going to redraw that table over here. Alright, so the next step, step 3, is to apply a column reduction. So in the first column, the smallest value that appears is 0. Same thing with the second column. In the third column, the smallest value is 7, and in the fourth, the smallest value is 5. So now we need to make those changes to each column. So there are no changes in the first 2 columns, they were both subtracted by 0. In the third column, we're subtracting everything by 7. And in the fourth, we're subtracting everything by 5, which brings us to this. So again, let's try and cross everything out, all the zeros out, sorry, with the smallest number of lines. Again, the minimum number of lines in this case is just 2, so we haven't yet satisfied the requirements to move to step number 7. So this is where we need to begin the actual process of the Hungarian algorithm. So using this third table here, we need to find the smallest uncovered number and add that to all covered numbers. We add it twice to any intersections. In this case, we have one intersection, which is at the number 2. All right, so the smallest number is 1. So I'm just going to write that here on the side here. So now I need to add that to all covered numbers except for number 2. I need to add it twice. All the uncovered numbers remain unchanged. So now I'm left with this table. My next step, so step number, what are we up to? Number 6, I think it is. Sorry, number 5, subtract the overall smallest number from all numbers in the matrix. So again, the smallest number here is 1. Often in steps 4 and 5, the smallest number is number 1. So we need to subtract that from every single number inside our table. All right, we've got quite a few more zeros now. We need to try and cover them with as minimum number of lines. Don't think it really matters which way I do this one. I won't be able to do it in less than 4, which is good. That's what we want. So that just tells me, yep, cool. We can do it in 4 lines for the 4 tasks. Now we can move on to drawing a bipartite graph and working out which programmer is going to do which task. All right, so on the left we had 4 programmers. We had A, B, C, D, Adam, Brad, Cameron, and Daniel. And we had just the 4 jobs, which we've just labeled as 1, 2, 3, 4. All right, so Adam, looking at the table to the right, had a 0 at jobs 1 and jobs 3. Brad had a 0 at jobs 1 and job 4. Cameron looks like the most talented. He had it at 2, 3, and 4. And finally, Daniel at job 1 and job 4. So this one has quite a lot of arrows here, quite a lot of connections in our bipartite graph. So we might have to test a few different situations depending on who's doing what. We can tell definitively that Cameron has to do job 2. He's the only one that has a 0 in that row. He's the only one that is connected up to job 2. So I'll write that up here, C2. With job 3, the only people that can do that now are Cameron and Adam. Because Cameron is already doing job 2, that means Adam must be doing job 3, which leaves us with jobs 1 and jobs 4. Now both David and Brad are doing those ones, or can do those ones. So it's a little bit of testing both. Which one renders us a more minimum time? So at the moment, with Cameron doing job 2, that's 13 weeks. With Adam doing job 3, that's 18 weeks. And then we've just got the 2 situations of Brad and Daniel doing jobs 1 and jobs 4. We just need to look at which one will work out better in the long run. And if it's the same, then we have 2 possible situations. So if Brad does job 1 and if Daniel does job 4, then the time for that will be 9 and 16 for a total of 25. If it's the other way around, Brad doing job 4 will be 15. Daniel doing job 1 will be 10, so it's also 25. So that is interchangeable then. So Brad and Daniel, it actually doesn't matter which one does job 1 and job 4. It works out the exact same. So in a question, we would just answer it like that. We could say that Brad has to do job 1 or 4, and Daniel has to do job 1 or 4. It doesn't really matter which one does which. Job 1 and job 4 over here we worked out was 25. Add that to Cameron and Adam's time. 25, 30, gives us a total of 56. All right, hopefully that clarifies a little bit. This is a very, very tedious and long process. So if you are still struggling, don't stress. Just keep asking for help, keep doing examples, and you'll get there. Thanks, guys.